Hello, everyone. I'd like to start off by thanking TGS for inviting us to speak here today, and by thanking all of you for joining in on this webinar. We're with Canadian Discovery, an independent, global energy information services company based in Calgary, and we're here today to talk about fluid dynamics data and ways in which this data can be incorporated into your team's workflow. My name is Allison Gibbs, and I'm a geologist with CDL who specializes in geomodeling and petroleum hydrodynamics. I'll be providing some background and workflows regarding pressure, temperature, and gas chemistry data. With me is Matt Baird, the IT and Data Director for CDL, who will be following up with a quick interactive tour of our new Fluid Dynamics Analytics modules available within our data analytics platform, part of our suite of subscription products as indicated on the slide. In our presentation today, we're going to be focusing in on the Montney Formation, which is located in Western Canada on the border between Alberta and British Columbia. Over the years, CDL has built up a significant library of work in the Montney Formation, and have been in communication with those working in the Montney about new ways of incorporating the available datasets to learn more about the formation. What we developed as a result of these discussions are two new Fluid Dynamics database modules. These modules are designed to provide up-to-date fluid dynamics data to the user, wherever they may be working from, and facilitate working at a variety of different scales, whether it be prospecting regionally or looking at development within a specific property. The Fluid Dynamics database currently includes curated and quality-controlled pressure, temperature, and gas chemistry data from within the Montney. However, since we have one of Western Canada's largest collections of integrated geoscience studies, we are currently making plans to expand our database to include a variety of fluids and formations. Before we dive into the data itself, I just wanted to provide a bit of background on hydrodynamics within the Montney and how this dataset fits into the bigger picture. Variable reservoir quality, multiple source rocks and phases of migration, and a complex structural history have all contributed to the Montney's complex hydrodynamic system. As you can see from this diagram, a more conventional system lies in the east, where hydrocarbon pools are contained within discrete stratigraphic and structural traps within the higher permeability reservoirs. In the west lies an unconventional deep basin-style hydrocarbon system, which is located in the lower permeability siltstone reservoirs. Here, an underpressured, oil-dominated fairway just west and down dip of the conventional system grades further down dip into overpressured liquids and gas fairways. From this diagram, you can see how the location of these transitions will vary with depth within the 4 Montney zones that can be mapped regionally. So now let's take a look at some pressure data within the Montney. Data supplied through standard vendors tends to be the pressure data obtained through the Alberta Energy Regulator or the BC Oil and Gas Commission. If we exported this pressure data as is and put it on a graph, it would look something like this graph on the left. As you can see, there's no way to differentiate the data either geographically or by zone. It's all Montney. There's lots of scatter. Without looking through the data in detail, it's tough to figure out what's usable. We don't know if the measurements are sufficiently built up or extrapolated, or if the data is affected by surrounding completions or production. So what's different about CDL data? First, wells are assigned to zones within a detailed, consistent stratigraphic framework that was built by CDL with renowned stratigrapher Graham Davies. We use surfaces from this framework to assign the wells to zones, but CDL staff is continually checking these assignments and adding tops to the database to improve the surfaces. Wells are assigned to pads, providing the ability to observe parent-child relationships and pressure effects on a pad basis and compare production between pads. Not only do we have regional hydrodynamic edges, but within those, we have geographic pressure plays that help describe the local pressure trend within a small geographic area. So why do we need to use this data? Lack of consistent and widespread direct data results in the need to incorporate indirect data for predictive purposes in order to mitigate development risk. So let's put that another way. Although there tends to be reporting issues with liquids production, if we take an area where the liquids production is relatively well reported and relate it to the gas chemistry, and then take the gas chemistry and relate it to the pressure and temperature environments that drive vapor-liquid equilibrium, this increases the amount of data we have to work with and can improve our capability to predict liquids distribution. For a good overview about our workflow for looking at these relationships from a regional perspective, please refer to SPE 196101 entitled Hydrodynamics, Geothermics, and Spatial Variations in Hydrocarbon Fluid Distribution within the Montney Formation. It has a detailed discussion on how regional pressure and temperature regimes are important to understanding the liquids distribution in the Montney and how these transitions differ between BC and Alberta. A key piece of this workflow is having a quality data set to work with, otherwise the results can't be trusted. Determining the quality of pressure data in low permeability reservoirs is more difficult than in higher permeability conventional reservoirs. As I mentioned previously, there are more scatter in the measured pressures. We don't know if the measurements are sufficiently built up or extrapolated. We also need to consider that within the lower permeability deep basin system, there are gradational changes in pressure, both laterally and vertically. During our regional Montney study, we came up with a way of looking at this from a more statistical perspective. Each test in our database has been assigned to a detailed geologic zone and corresponding pressure depth ratio map from the study. Then, within that zone, we've created small geographic areas or pressure plays. These are represented by the ellipses that you can see here on the pressure versus elevation graph. We're essentially dividing the data into smaller subsets and then determining the acceptable level of scatter within that smaller subset to quality code the data accordingly. If the measured pressure falls outside what we consider acceptable, then we give the test a U quality code so that we know to manually take a closer look at that test report. Within each well, we also highlight a maximum pressure where there are multiple pressures, providing the ability to easily evaluate pressure changes over time. This slide provides an example of a local case study from the Tower area in northeastern British Columbia. The graph in the middle shows the expected pressure depth ratio from the maps as compared to the calculated pressure depth ratio from the actual test data. The acceptable pressures with a B quality code are shown in green. The yellow and red pressure measurements fall outside the buffer. The yellow tests, which have lower pressures than expected, also had surrounding production prior to the test, so are flagged with a P for possible production-induced drawdown. The orange test gets a U flag, indicating that we should take a closer look at the test report. With the quality codes in mind, now let's look at the story behind this pressure distribution. As shown on the map, the green wells to the west were drilled in early 2017. The wells shown in yellow were drilled at the end of 2017, about 6 months after the first set of wells went on production, and these tested out higher tonnage and tighter cluster spacing. The wells farthest to the east were drilled in Q3 2018, and it seems that the operator had since adjusted their approach, drilling wells further apart and with cluster spacing similar to the first round of drilling. The longitudinal cross-section shows the contoured pressure depth ratios. The area affected by production-induced drawdown becomes more apparent when we contour it this way. In gas condensate reservoirs, pressure can be quite important in maintaining liquids production. Let's see if this area of decreased pressure is reflected in the liquids production. The cross-section at the top shows the condensate gas ratios for the first 3 months of production in these same wells. We do indeed see a similar trend reflected in the liquids production. We also see a similar trend reflected in the gas chemistry. This lower cross-section shows the C2 plus wet gas index, which is the percentage of gases with carbon numbers of C2 and heavier over the total. This value may provide a good proxy for the in situ hydrocarbon composition, since light alkanes do not seem to be strongly fractionated during the early production of hydraulically fractured wells. The map on the left is an example of a C2 plus wet gas index map, while the graph on the right shows an example of how these values support observed liquids production. This data is from a series of upper Montney horizontal wells where production is relatively well reported. Wet gas index is on the x-axis, condensate gas ratios are on the upper y-axis, and oil production is on the lower y-axis. At around 10%, or the yellow data, condensate production increases and is significant by around 15%, or the light green data. By around 20%, or the dark green data, the condensate production drops off and the wells are producing oil. Now that you've got a bit more background on the data and workflow, it's time to see something a little more interactive and to hear a different voice. Matt will provide a quick tour of the Fluid Dynamics Analytics modules within Catalyst, our data analytics platform that offers interactive mapping, graphing, and spreadsheet tools. At this point, I'll turn the mic over to Matt.
Thank you, Allison. Now I'm going to give you a live demo of some of the data that Allison has shown. Catalyst is our online analytical platform that showcases Canadian Discovery's data. For the purposes of this demo, I will be focusing on the hydrodynamics and the gas chemistry dataset. So the first thing I'm going to do is go into app mode and change this over to hydrodynamics. There are four main areas in this application. Over on the top left, we have the search area. There are several options to filter the dataset. Searching specific parameters, you can search for an individual well, or you can bring in a dataset. Searches can be saved for later use. On the bottom left is our map area. The top layer shows our pressure plays. After a search, wells will be displayed on the map. The top left displays our table view. Once a search is executed, this is where the data will be displayed. You can sort, change any of the headers to customize the list, and then save that as a template. You can also export all this data for use in any other program. Below is our graph area and chart area. This is where you can analyze the data with our custom graph options. For the purpose of this demo, I'm going to bring in a well list. First thing that you'll notice is the table view is now displaying the well data. There are 28 wells in this data set. The wells have also appeared in the map, and the map is zoomed in to show where those wells are. First chart I'm going to show is our pressure chart. I'm also going to choose quality code for our grouping. And as Allison had discussed, this is one of the things that Canadian Discovery does is we high grade these quality codes. So there were some U's in this data set that have now been switched over to D's. By improving this data, we allow for better analysis. The next chart I'm going to show is our depth chart. I'm going to change the x-axis over to longitude. I'm going to leave the detailed zone. All the Montney wells have been given a detailed zone by Canadian Discovery. If you press this play button up here, this shows the depth the wells were drilled to over time. Doing this can help you see trends in the data. For example, within a certain area, the focus may have started in the upper Montney, but over time, there may be opportunity in the lower Montney. The last graph I'm going to show is our advanced charts. What these do is they bring together the pressure and temperature data with the gas chemistry module, which I will show next. In this case, we will use our estimated reservoir temperature on the chart, which was calculated using our regional geothermal gradients, as DFITs being measured at the surface often incorporate a default reservoir temperature. So that's the default, and this is Canadian Discovery's estimated temperature. This again is another way Canadian Discovery improves the data set. Now I'm going to switch over our mode to gas chemistry. I'm going to bring in a different template for this. And again, you'll notice when I brought up the template, all the data loaded in the top right. All of these wells can be expanded to show if there's multiple tests. In this case, I'm going to expand this well. So this shows multiple chemistry tests, which can help you do some analysis over time. All of these headers that you see are some of the commonly used calculations with gas chemistry data, but we have access within our column chooser to add any of our other parameters. As you can see, there are quite a few. We also have some gas chemistry charts. I'm just going to leave it on the default, but there are a couple different ones that you can use. And that is the end of showcasing Canadian Discovery's Catalyst platform and our data sets. Thank you.
Thanks, Matt. I'm going to draw this presentation to a close with a slide summarizing some of the features of the Fluid Dynamics database. I'm hoping you found this presentation informative regarding not only the Montney Formation itself, but that it also has you thinking about how pressure, temperature, and fluids chemistry might be helpful in your workflow in any formation. Thank you so much for your time today. We're looking forward to hearing your thoughts and would be happy to answer any questions you may have.